So, we were talking about diagonalization of a real symmetric tensor. Now, first of all, when I say real and symmetric, we have already discussed that a moment of inertia tensor is both real and symmetric. Real because in a tensor, if it is all the elements, all the 9 elements in a 3D representation, a tensor has 9 elements. If all 9 elements are real, then it is a real tensor. Now, if I write the moment of inertia in a slightly different manner, if I write in a particular notation, which is I of ij, I and j being 2 indices, is sum over k m k, and it will be r k square delta I j minus r I r j, r of I and r of j. Okay. So, this is the form. Okay. So, this is a way we can represent a moment of inertia tensor. Let me explain. I and j, these are 2 indices, which, so I and j, okay, I will just put a line here. I j in this case can take values of 1, 2 and 3. I 1, or when I say, for example, r I, and if let us say I is equal to 1, so it will be r 1. So, r 1 means x, r 2 means y, and r 3 means z. So, this is just another notation, another type of representation we can use. So, the tensorial form is I of j I j, that means it could be you can read it as I x x, I x x will be I 1 1, I y y will be I 2 2, I z z will be I 3 3, and I x y will be I 1 2, I y z will be I 2 3, I z y will be I 3 2, and m k. So, there is another index which is a running index over this particular sum. So, m k corresponds to the mass of kth particle, and k can take values, once again k can take values of 1, 2 and 3. So, let us say sorry, my mistake. So, k can run over r k, sorry, this will be r k I, right, this will be r k I and r k. K can run over 1 to n, n being the number of particles in the rigid body. So, when I say, when we are measure, so this particular term actually measures the it's a metric which measures the distance of ith object, ith particle or kth particle from some fixed axis. Now, if I let us take an example, then it will be clear. If you take I equal to 1 and j equal to 1, then this will be I 1 1, which is equivalent to I x x, which will be equal to sum over k equal to 1 to n m k r k square minus r. Okay. So, r k 1 will be r k 1, r k 2, r k 3, r k 3 will be x k, y k and z k. So, r k 3 will be z k. So, kth So, this means the z component of the kth position vector. Okay. So, r k I will be r x, r k sorry r k of x, and r k j will also be r k x, right. So, it will be just k x. Oh, I am sorry, just made a mistake. So, it will be x k into x k, so x k square, right. And if I just replace this summation by integration, this will be nothing but integration rho dv r square minus x square, right. So, similarly, if I write it for I 2 3, which is nothing but I y z, now see what happens. Now, this summation, I am not writing the summation explicitly because the summation convention is in action. So, the so it will be m k. Now, I is not equal to j. So, then what happens? This delta I j, which is the Kronecker delta, I hope you are familiar with Kronecker delta. If not, I will just briefly tell you. So, I do not have any space, I can remove this, I think don't need any more, right. So, delta I j is equal to 1 if I equal to j, okay, and equal to 0 if I not equal to j. So, if I take I 2 3, that means I is not equal to j. So, this means this term will vanish, and r k 2 will be x y y k, and this will be y z, z k. So, this will be simply minus y k z k. Of course, there is a summation convention in action, and in integral form this will be simply minus rho dv y z, the standard form for I y z. So, this is a tensorial notation for the moment of inertia, right. So far we have wrote this expressions or this expression. I am putting everything together into single expression, which is this. So, keep this in mind. It looks a bit complicated in the beginning, but if you just look at it for some time, if you try to realize what these individual terms are saying, then you will immediately realize this term will come only if we are calculating the diagonal elements. So, that means when we are going along this, only then delta I j will survive, because delta I j also can be represented, it is also a tensor, okay, and this can be represented by this matrix 1 1 1 0 0. So, this is my delta I j in the standard 3-dimensional space we are working with, which is exactly equivalent to the identity matrix, which in some book people write with I, or in some time you will find this particular symbol also of 1 with an underscore. Okay. So, delta I j is nothing but the identity matrix. So, it is also a tensor of rank 2, and there we have two terms which can be represented, this combination can also be represented, shown to be a tensor of rank 2. Okay. So, this whole thing is a tensor. Now, once again there is no imaginary object here, none of this integration will lead to imaginary values, it has to be real, and most importantly it is symmetric, because if you change the indices I and j, if you, so right now we are calculating I 2 3, okay, I 2 3 is equal to I y z, okay, and this is exactly equal to I 3 2, which is I z y. So, I z y and I y z is equal. So, the upper half of this tensor is equal to the lower half. So, these two halves are identical. So, that is why it is a symmetric tensor. So, the tensor we are dealing with is a real symmetric tensor. Now, I think we are convinced that it is a real symmetric tensor, and we have already seen how does it transform under rotation. We have seen it here, that rotation in vector is r times a, and rotation in tensor is r transpose a r, or which is exactly equal to r inverse a r, right. So, we can either write transpose or we can either write inverse, which are same because we are dealing with a set of orthogonal transformation. Now, if you are really okay, so I will just focus on the diagonalization part now. What does it mean by this? Now, just a side note, in case you are interested to know more about orthogonal transformation, what it is, how it works, then I strongly suggest the book of Professor A.K. Roy Choudhury. It is a wonderful, wonderful book. There are only few pages on orthogonal transformation, but it is beautifully summarized. In this course, we will not have enough time to go into the details of orthogonal transformation, but right now we are going to discuss some aspect of it. Now, this transformation, what we wrote here, it's or we have it here, it's an orthogonal transformation because these rotation matrices, they correspond to a certain group of matrix, they they form a group which is called the orthogonal group. Okay. So, this is also called a similarity transformation. Because it's the matrices, they are working, very similar matrices work from left and right. Of course, there is a transpose sign, but this type of transformation, there is a mathematical name for it, is similarity transformation. Now, let us come to diagonalization. We are all familiar with the diagonalization of matrices. It does not matter if it is orthogonal matrix or symmetric matrix, real matrix, does not matter. We all know that diagonalization essentially means if we have a matrix A, then we can write A, what was it? Yeah, Ax equal to lambda x, right. So, this type of equations we are familiar with, and the next step is we write Ax minus lambda x, okay, determinant equal to 0, and this gives you a set of a polynomial which is called the characteristics polynomial. A is the typically what we take is A is a symmetric matrix or square matrix which is either 2 by 2 or 3 by 3 matrix. X is if it is a 3 by 3 matrix, then it is a 3 cross 1 column vector. If it is a 2 by 2 matrix, then it is 2 cross 1 column vector. So, most importantly, it is the square matrix, this is a column vector, lambda is a constant which is the eigenvalue, and this is the same x once again. So, we are familiar with this. Now, where is the rotation coming into it? The thing is, this type of operation is also a rotation. Okay. I cannot go into the mathematical details of it, which is very nicely worked out in Professor A.K. Roy Choudhury's book, Notes on Classical Mechanics. But what I can tell you, what do we do? What are the steps? We first solve this polynomial which is called the characteristics and we get, for let us say it is a 3 cross 3 matrix, let us assume that A is 3 cross 3, then we have 3 distinct eigenvalues by solving this equation, lambda 1, lambda 2 and lambda 3. That is what we have, right. This is a very standard procedure we are all familiar with. Next, what do? We take lambda 1, put it into here. So, we now come back to this original equation, we set A x 1 equal to lambda 1 x 1 and calculate x 1, find out x 1. And then we put lambda 2, okay, and then we try to find out an x 2 which is, if you recall, perpendicular to x 1. So, x 1 essentially means it is a vector direction. In the 3D space we are working with, it is a vector direction, right. Now, in that particular direction, we try to find out another direction which is perpendicular to the x 1 direction. That is what we do. And then we put x 3 lambda 3. So, we put x 3 equal to lambda 3 times x3, and we try to find out another vector direction x3. So, these are called these are eigenvalues, okay, and we have corresponding eigenvectors which are x1, x2, x3, and we try to calculate x1, x2, x3 such that the eigenvectors are orthogonal to each other. Orthogonal means what are the conditions? The condition is once again x1 dot, if I write it in vector notation, x1 dot x2 equal to 0, that is how, or x2 dot x3 equal to 0, x1 dot x3 equal to 0, or if we write in a general tensor notation, what we try to find out is xi xj once again is delta ij, where delta ij is a chronicle delta. Okay. So, this is the condition we impose. So, it is not only orthogonal, but when we put x1 square equal to 1, x2 square equal to 1, it remains orthonormal. So, not only orthogonal, but normalized to 1, the magnitude normalized to 1. That is exactly what we do in a matrix diagonalization exercise. Now, we have done that. We have done this many times without realizing this 3 sets. I mean, probably some of you have found it out or you know it already, but if you are not familiar, let me tell you that now what happens is, if I set, so see x1, x2, x3, these 3 are sets of orthonormal eigenvectors. They have, in the standard notation we follow, they have this particular form of either we take it as column vectors typically. Now, what happens if I form a matrix by placing x1, x2, x3 side by side? That means, I have, see, in x1, x2, x3 I have 3 column vectors, right. Now, what I do is I form a matrix where I put 3 column vectors side by side and make a 3 cross 3 matrix. That will happen. So, if I put 3 column vectors one after the other, okay, so we have 3 elements in each and we have 3 such vectors side by side, what we will have is essentially a 3 cross 3 matrix. Call it R. Okay, let us call it R. Now, do this operation on the original vector A. What was it? Ax equal to lambda x, right? That was the original equation we had, right? Now, let us assume, let us take this equation Ax1 equal to lambda 1 x1. This is also true because lambda 1 is an eigenvalue, corresponding eigenvector is x1. Multiply this with x2 transpose from left hand side and multiply. So, this will come here as well, x2 transpose x1. Okay. Actually, this condition, because two vectors cannot be multiplied unless and until we take transpose of first one. Okay. So, this condition will be xi transpose xj equal to delta ij. Use this condition here, what you will get is a 0, right, because x2 transpose x1 according to this particular condition will give you 0. But if I change it to x1 according to this condition, what will happen? If I multiply this with x1 transpose from the left hand side, the right hand side will give you lambda 1 only, right. Now, in this R, the first column is x1, second column is x2 and the third column is x3, right. Take transpose of R, what will happen? The first column, transpose means you are just interchanging rows and columns. So, here you will have x transpose in the first row, x1 transpose in the first row, second row will be x2 transpose and third row will be x3 transpose, is not it? Right. So, first column is x1. So, the after transpose the first row will be x1 transpose, second column is x2 transpose and x3 transpose. Now, do this operation, multiply this from left hand side, take the original vector original tensor or matrix A in the middle, multiply R from the right hand side. What do we get? Think of it now. Do this for any vector you are familiar with, or very for take any simple 3 cross 3 real matrix, do this operation. Matrix, the condition is there should be a set of orthonormal eigenvalues. Do this operation and you will see RT transpose A R will be nothing but lambda 1, lambda 2 and lambda 3. Just going by the same logic, because the multiplication will be such that only the diagonal elements will survive. Diagonal elements means you will be multiplying x1 with x1 transpose, x2 with x2 transpose and x3 with x3 transpose. It will give you lambda 1, lambda 2, lambda 3. Here we will have 0, 0 and here 0, 0, 0 and 0. Everywhere else is 0. So, this is essentially a diagonal form where we have eigenvalues in the diagonal and zeros otherwise. And let me tell you, going by this construction, we can generalize it for any dimension of matrix. We are just showing it for in a 3-dimensional case where we have x1, x2, x3, but if we are working in an n-dimensional space where we have n number of distinct eigenvalues and n number of orthonormal eigenvectors, this construction will always work. So, in this case, the final matrix will be an n cross n matrix, right. So, if we start with an n cross n A matrix, then essentially we end up with an n cross n diagonal matrix. Only thing is, only similarity is the diagonal matrices, so the final diagonal matrix will have the eigenvalues along its diagonal and everywhere else it will be 0, right. And that is where, so you see, as I said already, this is a rotation. This type of operation is essentially a rotation of a tensor. So, if a tensor is represented by a matrix in 3D space, and if we are doing this operation, that means we are choosing a suitable suitable rotation matrix in terms of R, which is happen to be the combination of the orthonormal eigenvectors, then we are essentially diagonalizing it. Now, physically what does it mean? Physically, it means, now let us go back to our original example of resistance. We took this object, right. So, this is our imaginary metal block. What we did was we applied voltage across it, we measured current, or let us say we applied a current in the x direction, we measured voltage drop across it in the x, y and z direction, applied a current in the y direction or z direction, measured the voltage across all 3 x, y, z direction, and constructed the resistance or resistivity tensor which has all these components. Now, if let us say this material, once again it is an imaginary metallic cube, it is not a metal, it is a cardboard box, it is a box which has chalks in it. Okay. So, if it is a, let us say if it is a metallic box and it has certain symmetric, molecular symmetry inside it, every metal has some crystalline ordering in it, right. Now, along certain ordered direction, it might so happen that if you apply current in that particular direction, that will affect only that direction. That means, you will have voltage only along that particular direction, not in any other direction, and that is reflected in the diagonal form. See, what happens in diagonal form is a matrix goes into this particular form, right. So, in general, if we have an n cross n matrix, we have lambda 1, lambda 2 up to lambda n, right. Now, you can write an equation. Now, let us take the case of, so moment of inertia tensor. So, moment of inertia tensor, let us assume there is some certain rotation for which it becomes I1, I2 and I3. Now, remember this equation L equal to I omega. What does it physically mean? Physically means if I break it into components, I have Lx, Ly, Lz and I have Ixx, Ixy blah 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 and Iyy, Izz. Okay, so there are two other components here and we have omega x, omega y, omega z. So, that means if I have a, so this was the reduction of this equation to begin with. Okay. The equation was Lx equal to Ixx omega x plus Ixy omega y plus Izz omega z. Similarly, we had equations for Ly and Lz. That means, if I have a velocity angular velocity component in the y direction, that will produce a angular momentum in the x direction. If I have an angular velocity component in the z direction, that will produce a angular momentum in the x direction, right. Now, what happens in diagonal form? Let us assume that we have somehow brought it into this particular form, okay. And in this particular form, if I have only I1, I2 and I3 and 0 everywhere, then my Lx will be I1 times omega x, Ly simply I2 times omega y and Lz simply I3 times omega z. So, that means we are bringing into a now rotation means we are moving the coordinate axis, right. That is what we mean by this. We are moving the coordinate system by certain amount and then we are bringing the, as we move on, as we are changing the coordinate, our the tensorial representation, the values in this tensorial representation also shifts, right. And so, essentially we can find out some coordinate axis in which it comes in a diagonal form. That means, in that particular coordinate system, if I have a rotational velocity component in omega x direction or x direction, that will produce an angular momentum only in x direction, not in y or z direction. Similarly, if I have a omega y component or if I rotate this object in that particular frame, particular x, y, z frame, if I rotate it only along y direction, that will produce an angular momentum only along y direction, right, no other direction. So, that is why for this we can also represent, we can also write omega 1 instead of omega x, omega 2 instead of omega y and omega 3 instead of omega z. So, these are this is a coordinate system in which we have this particular diagonal form of the moment of inertia tensor. That means, the angular momentum depends only on one component of angular velocity and no other components. And this particular set of coordinate is called the principal coordinate, and these three numbers of the this I1, I2, I3, which will be essentially the eigenvalues of the moment of inertia tensor, are called the principal moments of inertia. Okay. So, with this we end this particular lecture. We will continue from here in the next lecture. Thank you.